everyone. How's your Friday going? Oof. Not too bad. Good to hear. Oh, pretty good. It's Friday. It's Friday, so I can't be can't complain. Can't complain. Alrighty. Let's go ahead and get started. All right, so today we're going to finish up talking about using Lagrange multipliers to solve constrained optimization problems. And we're just going to do some more examples because that is the best way to learn to do these Lagrange problems. Okay. And this is the last material that will be covered on this upcoming exam on Tuesday. And yeah, I'll send out more emails as usual, reminding everyone of, exam time and process, and also the exam review we're going to have on Monday, and then practice problems, etc. And then I will, I'm going to try to write up the solutions tonight. If I don't finish, they'll be done sometime tomorrow. Yeah, and I'll have those uploaded so you'll be able to see not only the answers, but just how to work through the practice problems. Okay. So the setting for Lagrange multipliers is what we want to do is we want to find the extreme values of, so extreme values, it could happen that there's only a max or only a min or both a max and a min in these types of problems. So to find the extreme values of a function, so we want to maximize and minimize or minimize a function f of x, y, z, or f of x, y, if it's a function of two variables. And this is going to be subject to the constraint g of x, y, z equals k. So the constraints, usually, often with the problems, we're not going to be given everything in exactly these words in the problem. We're not always going to be told, here's the function you're going to maximize. So for instance, for the volume of the box, we had to come up with a function to maximize, right? We needed to write the dimensions of the box as x, y, and z, and then the volume becomes x times y times z. And we're often not going to be told subject, in these exact words, subject to the constraint g of x, y, z equals k. So for instance, in the box problem, our constraint was that we only had, I think it was 10 square feet of cardboard, which is actually a lot of cardboard, but ignore that. So we had 10 square feet of cardboard. That was our constraint. And we had to translate that into a constraint equation. Well, the amount of cardboard you use is the surface area of the box. So we had to write the surface area in terms of x, y, and z and set it equal to 10. So we did an open top box that was the 2xz plus 2yz plus xz equals 10. That was our constraint equation. Sometimes, as we'll see later, you're also given a problem like maximize and minimize this function on, say, like the circle x squared plus y squared equals 1. So another way of thinking of the constraint is the constraint tells you the set of points we're looking at where we want to maximize and minimize our function. So if you want to maximize and minimize a function on, say, some curve in R2, and that curve is, say, the circle x squared plus y squared equals 1, that's your constraint. That tells you the set of points you're considering. And so that's another way the constraint equation pops up. And we'll see an example of that in a sec. OK, so if we want to do that, so we want to maximize and minimize a function f subject to some constraint g of x, y, z equals k. We want to find all x, y, z, and lambda, satisfying the gradient of f at x, y, z is equal to lambda times the gradient of g at x, y, z. And those are actually 3 equations there. You set each partial equal to each other. F sub x is equal to lambda g sub x, f sub y is equal to lambda g sub y, etc. And also the constraint equation, g of x, y, z equals k. So find the x, y, z, and lambda. Usually we don't think too much about lambda, except for lambda equals 0. Satisfying all those. So the x, y, z are going to give you a set of points. Maybe only one, but maybe a few. Oops. So we want to look at the value of the function at each of those points. And the largest value we get is the max, of course, and the smallest is the min. Sorry, in case that's completely legible, that says the largest value is the max, etc. The smallest is the min. So we set up these equations, find our x, y, z, and sometimes lambda. And then that gives us a set of points. We check the value of f there. The biggest value we get is the max, the smallest is the min. OK. Here's another common type of example. And this is going to show one useful, very, very useful thing to know when doing these types of problems. It's going to make your life a lot easier. So let's find the point on the plane x over 2 plus y over 4 plus z over 4 equals 1. Which is closest to the origin. OK, so again, we're not explicitly given things in this language here. We're not told to find the extreme values of this function subject to this constraint. we have to figure out what those are in this case. Okay, so first order of business, what is it we want to maximize or minimize? In words.
You want to minimize the distance to the origin?
Right, we want to minimize the distance of a point to the origin. Okay, so if we have a point x, y, z, what is the distance of x, y, z to the origin mathematically? Well, the origin 0, 0, 0. What's the distance between the point x, y, z and 0, 0, 0? Right, it's the square root x squared plus y squared plus z squared. Okay, so you could use this function, but what we're going to be doing is we're going to be taking the partial derivatives of this function. And when we do that, things are not as pretty as they could be, right? Because of the square root, right? So when we take the partial with respect to x, we're going to end up getting x over square root x squared plus y squared plus z squared. It's not going to be very nice to deal with. So what we're going to do is we're going to get rid of the square root. Seems like cheating, but it makes sense. And here's why. So what we want to do is we want to find the closest point to the origin. In other words, we want to find the point. So this point, if you pick any other point on this plane, then the distance between that other point and the origin is more than the distance between this one point and the origin. That's also true about the square of the distance. So let's say suppose ABC is our closest point, right? So if we pick some other point x, y, z, if that point is further away than the point ABC, in other words, if the square root of x squared plus y squared plus z squared is more than, let's just say bigger than, the square root of a squared plus b squared plus c squared, then the same is true for the square of the distance. Right, so if the distance of a point to the origin is bigger, then so is the square of the distance, and vice versa. If the square of the distance is bigger, then the distance is bigger also. So the point which is closest to the origin is going to minimize this function, but it's also going to minimize the square of the function. And the reason that's nice is we get rid of the square root, and then taking the partial derivatives is much nicer. So we're going to let our function be the square of the distance, x squared plus y squared plus z squared. So this is the function we're going to minimize here. We're allowed to do that because the point that minimizes this function also minimizes the actual function we want to deal with. But x squared plus y squared plus z squared is going to be nicer to deal with than the square root of x squared plus y squared plus z squared, because we don't have to deal with the square root when taking partial derivatives. So let me just say, if you want to maximize and minimize a function that involves a square root, if it's like a square root of a whole thing, you can just maximize and minimize the square of that function, and you'll be fine. Well, okay, so that's not always true, but it is true for distance, and that's usually what we're going to deal with. So does that point make sense? Because that's kind of an important one. So the actual function we want to minimize is square root x squared plus y squared plus z squared. Don't like the square root, so we're just going to square it and minimize x squared plus y squared plus z squared instead. We're going to come up with the same point that minimizes that. And that's all we care about. And this is going to be a lot easier to deal with. And that's the kind of thing, that's what you want to do every time you're dealing with like a distance problem. Okay, so that's the function we're going to minimize. And what is our constraint? So remember, another way of thinking of the constraint equation is it tells you the set of points we're considering. So we're not looking for the point closest to the origin out of every single point. I mean, that's obviously just the origin, right? That would be a boring problem. We're looking for the point on the plane, x over 2 plus y over 4 plus z over 4 equals 1, closest to the origin. So the equation of the plane is telling us the set of points we're considering, because we're only considering the points on that plane. So our constraint equation, whoops. So our g of x, y, z is x over 2 plus y over 4 plus z over 4 equals 1. So our g of x, y, z, the left-hand side of the plane equation, and it's going to be equal to 1. Okay, everyone comfy with this, because if you can't get this bit set up, you're hopeless to solve the problem. You don't even know where to start. Okay, so we got our function we want to minimize and our constraint equation. So let's set up our 4 equations here. Oops. I'll just write those down again. So our f of x, y, z is our x squared plus y squared plus z squared. And our g of x, y, z, oops, is our x over 2 plus y over 4 plus z over 4 equals 1. Okay. So we have the gradient of f equals lambda times the gradient of g. In other words, f sub x is equal to lambda g sub x, f sub y is equal to lambda g sub y, f sub z is equal to lambda g sub z. So what's the partial of f with respect to x? Two x, all right. So 2x, which is f sub x, is equal to lambda times g sub x. What is lambda times g sub x? Or what is g sub x? Just 1/2, right? So lambda times g sub x is just lambda over 2. Then do the same for f sub y and lambda g sub y. So our f sub y is 2y. Our lambda g sub y is lambda over 4. Our f sub z is 2z. And our lambda times g sub z is lambda times 1 over 4 also. And then our constraint equation was, of course, the x over 2 plus y over 4 plus z over 4 equals 1. Okay, so those are our equations. We're going to look for lambda, x, y, and z, whoops, satisfying these guys. Okay, so remember, whoops, last time I said, always check for lambda equals 0 ahead of time, because it's usually going to work differently than lambda non-zero. And it's something you need to either find the points corresponding to lambda equals 0 or rule out lambda equals 0. That should just be step 1 always when you're solving these. So let's see, can lambda equal 0? So if lambda is equal to 0, what does that tell us about x, y, and z? So if we look at the first 2 equations, lambda equals 0 tells us x, y, and z are all equal to 0. And if x, y, and z are all 0, can that satisfy the constraint equation? No, it doesn't. Right? You plug it in, you get 0 equals 1, which is not the case. So 0, 0, 0 is not on the plane we're considering. And so lambda can't be 0. So there are no points corresponding to lambda equals 0. Now we can just assume lambda is not 0 and then kind of forget about the actual value of lambda. Okay. So now we're going to assume lambda is non-zero. All right. So we want to get a relationship. So there are 2 ways to do this. What we could do is we could get lambda by itself for each of these, and then solve for lambda explicitly at the end, and then plug lambda in to the first 3 equations to get x, y, and z. Right, so the first equation, we could get lambda by itself, and we'd say lambda is equal to 4x. The second equation, we could solve for lambda. Lambda is equal to 8y. Oh, sorry. No. We would get, we get x, y, and z by themselves and write them in terms of lambda. Right, so we could say x is lambda over 4, y is lambda over 8, and z is lambda over 8. And then go to the constraint equation and replace x, y, and z with their corresponding expression in lambda, and then solve for lambda, and then plug that lambda back in. That works just fine. What we're going to do is we're going to kind of skip a step, and we're going to get a relationship between x, y, and z, and it'll be slightly faster. But honestly, they're both equally easy to do. Okay, so we're going to get the same thing on the right-hand side everywhere. So what we're going to do is we're notice on the right-hand side, the second two equations both have lambda over 4. So we're going to get lambda over 4 on the right-hand side of the first equation. So we're going to multiply both sides by 1/2. Hang on. So 1/2 times 2x equals 1/2 times lambda over 2. So we got x is equal to lambda over 4. And then we also have 2y is equal to lambda over 4, and 2z is equal to lambda over 4. So x, 2y, and 2z are all equal to the same thing. So let's write them all in terms of z. X is equal to 2z. And we also have 2y equals 2z. In other words, y is equal to z. Does everyone see this? What we're doing is we're writing each variable, we're writing x and y in terms of z. And so then we're going to go to our constraint equation, and everywhere we see x and y, we're going to replace it with the corresponding expression in z, and then we're going to solve for z. So x is equal to 2z. That's what we're going to place in the constraint equation. Y is equal to z. So let's plug those in. Into there. And when we do that, we get 2z over 2, which is z, plus y is equal to z, so z over 4, plus z over 4 equals 1. How did I get those values I circled? So what I did was I looked at these equations. Maybe the solving for lambda or writing in terms of lambda would have been maybe a little more straightforward, but this is what I did. So we looked at these first three equations, and we noticed that the right-hand side is almost equal in all these. The second two, we have lambda over 4. First one, we have lambda over 2. I can get lambda over 4 there if I just multiply both sides of the first equation by 1/2. So I did that. Now all the right-hand sides are equal to each other, and then I can set the left-hand sides equal to each other. So I know x now is equal to 2z, and 2y is equal to 2z. In other words, y is equal to z. Yeah. So I'm using that to get a relationship between x and z and y and z. Okay. So z plus z over 4 plus z over 4 is equal to 1. In other words, we have 3z over 2 is equal to 1. So z is going to be 2/3. And we know y is going to be equal to z, which is 2/3. And we know x is going to be equal to 2 times z, which is 4/3. So we only get 1 point here. And it makes sense because we're not actually going to get a maximum of this function, right? There's no, if we look at a plane, there's no point you can point to which is the max distance away from the origin, because the plane just keeps going off to infinity, right? You can find points arbitrarily far away from the origin. So there's not going to be a max. The one point we find is going to be the minimum distance to the origin. So that 4/3, 2/3, 2/3 is going to be our closest point.
How did you get 2/3?
So we solve for z here by plugging those relationships into the constraint. So we got z plus z over 4 plus z over 4. So z plus z over 2. 3z over 2 is 1. And so z is 2/3. Does that make sense? So there are like different ways to do that first step, dealing with the partial derivative equations. There are many different ways to do that, but in the end, usually we're going to either write two of the variables in terms of one, say like x and y written in terms of z, or we're going to write all the variables in terms of, say, lambda. And then the next step is always the same. We're going to use that relationship we get from that and plug it into the constraint equation, and then solve for either that one variable or lambda. And then when we do that, we're going to plug those whatever solutions we get back into the relationships we found earlier to find our points. Sorry, so that is the closest point we're looking for. So it didn't actually ask for the distance of the closest point, but if you wanted to, you could just plug that back into the distance formula. But yeah, I believe it's 5/3 is the distance. No. Sorry, square root 27 over 3. Oh, distance is 3. Okay, yeah. Any questions about that example? We'll do one more. Okay. So let's find the max and min of the function. Now we're going to do one of two variables, 4x squared plus 10y squared on the disk x squared plus y squared less than or equal to 4. Okay. So let's draw a picture real quick, and let's explain what's going on here. So it turns out we're going to use Lagrange in this problem, but using Lagrange is not enough to solve the entire problem. We're going to have to do more than that. Okay, so the disk x squared plus y squared less than or equal to 4. So x squared plus y squared equals 4 is a circle centered at the origin of radius 2 in R2. Less than or equal to 4, the disk is everything inside of that circle, including the boundary circle. So equals 4 is the boundary circle itself. Less than or equal to 4 is everything inside of there. Okay, so we're back to the previous chapter where we wanted to find the max and min of a function of two variables, the absolute extreme values of a function of two variables on a closed bounded set in R2. Right, some solid region in R2. And remember, remember the way we do that is step 1 is we're going to find the critical points of F in the interior of this guy, or the critical points which lie inside of here. And then we're going to check F there. And then step 2 broadly, we broke it up into different ways last chapter, but we're going to find the max and min of F on the boundary. Whoops. Okay, so what is the boundary of this guy? Well, the boundary is the circle x squared plus y squared equals 4. The way we did this before is before we knew about Lagrange, so we couldn't write the circle. We'd have to break it up into 2 bits. The top half we could say y is equal to square root 4 minus x squared. The bottom is y is equal to negative square root 4 minus x squared. Then we transform our function, find the critical points, et cetera, check the corners where the 2 pieces meet. But it turns out we can actually use Lagrange to find the max and min on the boundary in this case. And that's what we're going to do here. So one thing I want to note is, so if you only use Lagrange in this problem, you're not going to get the correct answer. You're going to be missing, in this case, where the minimum happens, because you're only going to be considering points on the boundary. So I want to say, for Lagrange, if you're given an equation for the set of points you're considering, for Lagrange, you need an equation. You need an equal sign. If you have an inequality, then you're going to have to be doing what we're doing here. You're going to have to find the critical points. What you're going to do is you're going to get like a solid region, right? The boundary of that guy, you're going to use Lagrange. You can write the boundary using an equation, In this case, the x squared plus y squared equals 4. But then you need to consider the points inside of there, the solid part. And for that, you're going to have to find the critical points of the function inside of there. So the inequality here means we can't just do Lagrange. We have to do the step 1, which is find the critical points of f in the interior of this guy. And then we use Lagrange for the boundary, which we can write using an equation. Does that, any questions about that? Okay, cool. So step 1. So the function f of xy, 4x squared plus 10y squared. Let's find the critical points. So we set both partials equal to 0. What's the partial of f with respect to x? Well, that is 8x. Set it equal to 0. The function we want to maximize and minimize. The partial with respect to y is 20y. We set that equal to 0. What can we deduce from this? What is our critical point, or what are our critical points? Only 0, 0, right? So the first equation tells us x has to be 0. The second tells us y has to be 0. So 0, 0 is our only critical point. Remember, we need to make sure that our critical point is inside the region we're considering, right? So if we got like the point, 10, 0 or something like that, like way out here, we don't count it because it's not in the region we're considering, but is 0, 0 inside of the region we're considering. We'll call this guy D. It is indeed. If you're unsure if a point is in there, use that inequality, the x squared plus y squared less than or equal to 4, plug in your x and y values and see if it satisfies the inequality. If it is, then it's in our region. So then we check the value of our function there, f of 0, 0, and we get 0. So we're going to add that to our list at the end. And the biggest value on the list is going to be the max, the smallest is going to be the min. Okay, so that is the critical points inside of our region D. Okay, so step 2, we saw a different sort of more difficult way of doing this last time. I would suggest just using Lagrange here. And anytime we have any of these find absolute max and min value of a function on some closed bounded region, you can use Lagrange on the boundary if, let me write this. You can use the Lagrange to find the max and min on the boundary if you can write the entire boundary using a single equation. Let me say it this way. If the boundary curve has a single equation. So in this case, our boundary curve is the circle x squared plus y squared equals 4. That equation, x squared plus y squared equals 4, is the equation for the entire boundary curve. Because that's the case, we can just use Lagrange, and it'll actually be easier than breaking it up into two pieces and doing the process we did before. However, if you have, say, like a triangle or something like that, then you're going to have the boundary consists of three pieces, the left, the bottom, and the right. And each of those three are going to be curves with different equations. And so you would actually have to do Lagrange 3 times. I would suggest not doing that. I would suggest doing the old thing if the boundary consists of like multiple pieces and each of them have like different equations. Does that make sense? But since the entire boundary we can write as a single equation, we can think of this as maximizing and minimizing the function f subject to the constraint x squared plus y squared equals 4. So we're going to find the max and min on the boundary. So we're going to find the extreme values of f of xy, which we said was 4x squared plus 10y squared. On the circle, this is the boundary, x squared plus y squared equals 4. Yes. Okay, so our f of xyz, or sorry, our f of xy is 4x squared plus 10y squared. That's the function we want to find the extreme values of. And our g of xy is going to be the x squared plus y squared, and that's equal to 4. That's our constraint equation. So let's set up our equations. So you have the partial of f with respect to x, which is 8x in this case, is going to be equal to lambda times the partial of g with respect to x. So g of xy is x squared plus y squared. So lambda g sub x is lambda times 2x. Then we do the same for y. F sub y is 20y. Lambda g sub y is lambda times 2y. And since it's a function of two variables, the gradient, setting the gradients equal, is only going to give us two equations. So then we also have the constraint equation. Let me give myself more room here. So g of xy is, sorry, x squared plus y squared equals 4. So you don't have to write out the f sub x, the lambda g sub x explicitly. I'm just doing that so everyone knows where these equations are coming from. But these are the equations we're going to consider. Okay, so as always, we consider the first set of equations to get a relationship between x and y, or to write them in terms of lambda, so we'll see, or to do some other stuff. And then we use that info and plug them into the second equation. Okay, so first thing we're going to do is check, can lambda be 0? Either really quickly rule it out or figure out what points correspond to lambda equals 0. So if lambda equals 0, then x and y are both 0. Plug those into the constraint equation. So lambda cannot be 0. So now we're going to assume lambda is non-zero. It turns out the way we're going to solve this, we didn't really need to do that, but it's a really quick check. And it's a good thing to get in the habit of doing. OK, so 8x equals lambda times 2x, 20y equals lambda times 2y. OK, so what we're going to do is let's look at this first equation. Let's get everything on one side. And then let's see what this says about x or lambda. OK. So let's simplify this guy. So we can pull out 2x. So 2x times 4 minus lambda is equal to 0. So this first equation tells us either x is equal to 0 satisfies this, or lambda is equal to 4. OK. So what we're going to do is we're going to use, in each of these, we're going to see what this implies about y. Let me give myself more room here. So either x equals 0 or lambda equals 4. OK, so if x equals 0, that doesn't tell us anything about y. The second equation, we can't figure out what exactly that tells us about y from the information that x equals 0. But we can find y by plugging x equals 0 into the constraint equation. And when we do that, we see 0 squared plus y squared equals 4. Y squared equals 4, so y is equal to plus or minus 2. So we get the points x equals 0, y equals 2, x equals 0, y equals negative 2. And we'll come back to those in a sec. OK, so the second one, lambda equals 4. So if lambda equals 4, that doesn't tell us anything about x, but we can go to the second equation, and we see that from the second equation, we get 20y is equal to 8y. And so that only happens when y is equal to 0. So plugging that into the constraint equation, if y equals 0, we get x squared equals 4. So then x is plus or minus 2. And so from that, we get the points x is 2, y is 0, and then x is negative 2, y is 0. Okay. So now we got 4 points. You could do the same thing for the second equation. It turns out you're going to get exactly the same points. So you really only need to do this for the first equation. I won't explain why, but that is the case here. Okay, so we got 4 points, 0, 2, 0, negative 2, 2, 0, and negative 2, 0. We're going to check the value of our function at each of those. The biggest is going to be the max on the boundary. The smallest is going to be the min on the boundary. So when we plug those in, so our function was 4x squared plus 10y squared. And that's the same for plus or minus 2. And when we do f of 0 plus or minus 2, we get 40. Okay. So we add those values to our list. And then step 3, we compile everything from steps 1 and 2. So step 1, we got the critical point. The value of f there was 0. Step 2, we got the values 16 and 40. Max is going to be the largest, which is 40. And the min is going to be the smallest, which is 0. Okay. So to reiterate, we had an inequality. So we have to do the process for finding the absolute max and min on a closed bounded region in R2. So we find the critical points in the interior of this guy. And then step 2 is we find the max and min on the boundary. We can write the boundary curve as a single equation. So we can use Lagrange for the boundary thing instead of breaking it up into pieces and checking the corners, et cetera, et cetera. So we got 0 at the critical point, 16 and 40 on the boundary. Biggest is 40, smallest is 0. Okay. Any questions about today? All right. If not, have a great weekend. Go ahead and get to working on those exam review questions, and I will get the solutions together, and I will see you on Monday. Have a good one, guys.
Thank you.